For every single second of human history, all our eggs have been in one fragile basket. Earth is perfectly tuned for our biology, but it remains highly vulnerable to a single extinction-level event. To guarantee the long-term survival of our species, we have to build an interplanetary insurance policy. We need to spread out. This transition is already beginning. Within the next decade, we will see the launch of commercial space stations and the foundations of a permanent lunar base. But getting there brings up a massive physical conflict. The vacuum of space is an inherently lethal environment, almost as if it were optimized to destroy the human body. Becoming a multiplanetary species requires more than bigger rockets. It demands a ground-up redesign of our buildings, our medical systems, and even our social structures. The first major hurdle is basic logistics. Launching heavy, dense materials like steel and concrete into deep space is physically and financially impossible. For early orbital stations, engineers bypass mass limits using expandable modules. These habitats launch packed flat, then mechanically inflate in orbit to maximize living volume. But when it comes to permanent bases on the Moon or Mars, we have to use something called in situ resource utilization, or ISRU. This animated diagram shows how it works. We collect local Martian soil, regolith, bake it down, and run it through a 3D printer apparatus to lay down structural brick habitats on site. True interplanetary architecture requires us to build cities out of the dirt of these new worlds, permanently severing our reliance on Earth's supply chain. Then there is the biological bottleneck. A human silhouette in microgravity shows a rapid loss of bone and muscle. Past Earth's magnetic field, cosmic radiation continuously penetrates the body, degrading cellular structures. If someone gets severely injured or sick in deep space, packing a fully equipped hospital or a freezer full of biological tissues into a rocket simply won't work. Engineers are developing techniques to 3D bioprint biological materials. High-tech nozzles will precisely print layers of living tissue and bone structure right where it's needed. Sustaining life millions of miles away means replacing traditional medical supply lines with on-demand biological manufacturing. Even if the physical body is protected, the mind remains vulnerable. Simulated Mars missions consistently show that human psychology is highly susceptible to breakdown under extreme isolation. The total absence of nature, combined with a severe lack of direct social contact, acts as a hidden killer for long-term crews. To prevent this, next-generation orbital outposts are incorporating biophilic design. The interiors feature lush green gardens, natural lighting, and open communal spaces. These future habitats cannot be bare metal survival capsules. They must be carefully engineered to simulate Earth-like normalcy and community, ensuring crew sanity. The first commercial modules for these orbital cities are already in production, and mapping missions for permanent lunar landing sites are currently underway. NASA's Artemis program represents the immediate, tangible stepping stone toward building this deep space infrastructure. The extreme constraints of the space environment force engineers to invent systems that operate with near-zero waste, efficiency levels that are rarely prioritized on Earth. These space-driven innovations have immediate, practical applications back home, from highly advanced remote medical treatments to ultra-efficient closed-loop water and air recycling systems. The effort to build a backup for humanity on the Moon and Mars acts as a stress test for our engineering. The tools we develop to survive the absolute scarcity of space will dictate how we manage the tightening resources of our own planet.